So our presentation is on ciphers. So basically, what is a cipher and how do they work? So basically, if you look at the diagram, you'll see that a cipher is essentially the transformation represented by an encryption function and its corresponding decryption function. So how do encryption functions and decryption functions work? Basically, you have a message, some message that you want to send in plain text, which is essentially just the regular how the message is formatted before you encrypt it. And you are trying to send it, but you're trying to send it over an insecure network. So you need to basically encrypt it and make sure that whoever could access the message wouldn't be able to translate it or understand it. So the way that that's done is through encryption. So basically, you have your message, you have your plain text, and you encrypt it using something called an encryption key. Once you encrypt it, that message is now in ciphertext because it's untranslatable, and you send it over the insecure network, and the receiver receives the message in ciphertext, not plain text, because it's been encrypted. They are able to decrypt it using their decryption key, and they can now read the message in plain text.
So, block ciphers. What are they? Block ciphers are an encryption method that are able to use an algorithm along with a symmetric key in order to encrypt a whole block of text. So, how does it work? The way that I started to think about it is kind of like a function. So let's take the formula y equals mx plus b. So you can think of x as your input. You can think of m as the encryption that's being performed on the input. And you can think of b as your initialization vector, aka which like level of the encryption you're going to be doing. So if we look at this text over on the right here, well, let's start with the text, the red text. So plain text would be your block of text, right? And as you can see, the M being performed or the encryption being performed is to move the data like over one, right? So +1. And on the left, you can see your keys, which tell you which level of encryption is being performed to that block of text. And you can see like you have 1 right here where everything is moved to the 1 over 1. And then from there, everything else is moved over 1 more. This is also illustrated in our text in our picture on the left, where you have your initialization vector. And then once you perform an encryption, you take that value, make it your new initialization vector, and then perform it again on the next block of text. So this is an example of cipher block chaining, where each block that is chained becomes a new initialization value for the next block trying to be encrypted. And you also have another augmentation called counter mode, where, as you can imagine, if you were to only go up each encryption by 1 for like the initialization vector for each block that you're cipher or encrypting, if a hacker were to find out 1 block, it would be very easy for them to figure out the next block, right? Well, with counter mode, you can have it go up by 2, 3, 4. So just because they figure out how to unencrypt one or decrypt 1 block doesn't mean they're going to figure out every single encryption for every single block. So the criteria to make a block cipher is that it must be a permutation, meaning that whatever is done needs to be able to be undone. And of course, this makes sense because once you encrypt something, you also want someone to be able to decrypt it. People are supposed to read the file. And going back to thinking of it like a function, I would say a way that I thought about it was y equals mx plus b. That can be undone, correct? But let's think of a derivation, for example. That is you can't really undo a derivation. So whatever is done to the encryption needs to be able to be undone to decrypt it. Another criteria is that it must be very efficient. So, stream ciphers. As opposed to block ciphers, a stream cipher encrypts each plain text digit rather than the whole block. It does this by combining the plain text with the pseudo-random key stream, which allows for each digit of the plain text to be encrypted with the corresponding key stream digit. So while that sounds like a bunch of jargon, I'm going to use the example to break it down step by step. So if we look at the picture I provided, we have our original plain text. This is what we're trying to encrypt. So we can convert this to numbers, and then we have our pseudo-random key stream. I want you to focus on the word pseudo-random because that's going to be important later in explaining the downfalls of stream ciphers. But so we have our pseudo-random key stream, and we are also going to convert that to a number. So then we add the two together and we get our ciphertext, aka our encrypted plain text, and we're going to wrap that so that it cuts off at 25. And then once a number reaches 25, like the second value t, it becomes a 2, because if we wrap it to 25, we can convert it back into text, and then we get our encrypted text. And again, if we wanted to decrypt it, all we would need to know is what like we wrapped it to, and also our pseudo random key stream, and then we could undo everything we've done and get our plain text again. So the pros of using stream ciphers is it's really good for real-time hardware or real-time information, things that are coming in one bit at a time. You can encrypt it as you go. Cons would be software applications, because if you were to download that and it comes into pre-spaced blocks, it'd be easier to encrypt the blocks or use like block encryption that encrypts the size of data that's already coming in. Another big con for stream ciphers is security. So like I said, you're using a pseudo random key stream. So if we're using a random number generator or letter generator given by like a public generator, if people figure out what generator you're using and what algorithm your pseudo random key stream is being generated in, they could use that in order to decrypt your data. So in order to have the most secure stream cipher, you would want to have a pseudo random key stream that you are only going to use once for this project and that other people don't know you're using. So that way they could not use like the number generator and figure out the algorithm in order to decrypt your data without your knowledge or your permission.
So ciphers can also be categorized based off of the type of key there are. So based off of that measure, there's secret key ciphers and public key ciphers. Secret key ciphers are ciphers where both participants share the same encryption key. So basically the encryption key and the decryption key are the same thing. The US National Institute of Standards and Technologies has standards for a series of secret key ciphers that they've approved. The first one was called DES. DES is still works in the sense that no cryptanalytic attack better than brute force has been discovered that can crack DES. But unfortunately, because the speed of computers and the amount of computers available has increased, you can crack DES with brute force. So the fact that you can't crack it in any other way doesn't really matter anymore. Therefore, DES is considered outdated, but it's still important to learn about it because it is a functional method of encryption. So originally it was designed by researchers at IBM in the early 1970s. It was adopted by the US government as an official federal information processing standard in 1977 for the encryption of commercial and sensitive government computer data. So how does it work? To encrypt a message, DES groups the message into 64-bit blocks. Each block is enciphered using the secret key into a 64-bit ciphertext by means of permutation and substitution. And that process involves 16 rounds and can run in 4 different modes, encrypting blocks individually or making each cipher block dependent on all the previous blocks. The way decryption works is essentially just the inverse of the encryption, so following the same steps but reversing the order. So DES uses a 64-bit key, but 8 of those bits are parity blocks. So essentially it's using a 56-bit key, which means that it would take a maximum of 2 to the power of 56 attempts to actually find the correct key, which is a massive number. But again, because of the sheer amount of computers that are available now and the speed at which they can run, it's a number that you can crack. So another form of cipher is called triple DES, which is basically, which works better than DES, but it is only approved through 2030. So the way triple DES works is it essentially works the same way as DES, except it has 3 keys instead of 1. So a triple DES key has 168 bits and it's chunked into 3 DES keys. For our purposes, let's call them DES. Let's just call them key 1, key 2, and key 3. Um, DES encrypts the block of plain text by encrypting the first block using the key 1, and then decrypts that block with key 2, and then encrypts it again with key 3. And decryption is essentially the inverse. So it's decrypted with key 3, encrypted with key 2, and then decrypted with key 1. So it does work because it essentially just compounds DES. But the Institute of Standards and Technology has found a more effective method because that one can be a little bit slow. So that method is called AES, and it was established nearly 20 years ago to replace DES. AES encryption keys go up to 256 bits, whereas, like I said, DES keys are 56 bits. While the data blocks are broken up into 128 bits, the key sizes can vary in length. So they can be 128 bits, 196 bits, and 256 bits. So how does it work? AES essentially uses 4 scrambling operations per round, and the number of rounds of encryption depends on the length of the key. So like I said before, there's 3 different key lengths, 128, 192, and 256. So basically how it works is, say you start out with a plain text X, and then it goes through a round, it would be scrambled 4 times, and then what comes out would be Y. So that process essentially will happen 10 to 10, 12, or 14 times depending on the number of bits. So 128 bits has 10 rounds, 192 has 12, and 256 has 14, which is really impressive because that makes the number of combinations to break AES 2 to the power of 256, which is a bigger number than 2 to the power of 250, or which is a bigger number than 2 to the power of 56. And it would take longer. It takes much longer and is currently impossible to crack that just using brute force. So it is the current method of secret key cipher recommended by the U.S. National Institute of Standards and Technology.
So, public key ciphers. How do they work? So it uses a pair of keys shared by 2 participants but owned by 1. So the person who owns the public key can write encrypted messages to the owner who owns the decryption key, which is the private key that nobody has but them. And this allows them to decrypt any of the encrypted messages that they receive. It doesn't matter how many people have a public key and send encrypted messages to the private key, but only one person should have the private key or the decryption key. So the advantages of this is it allows for secure one-way communication and kind of gives a digital signature to whatever's being sent to the decryption key. However, a more interesting way to use public key ciphers is with two-way encryptions. This allows for complete confidentiality messaging both ways. So the way that this works is a little bit complicated, but we can break it down as if you have person A and person B. Each person has a private key and a public key, and a private key and a public key. So how this works is, say person A wanted to message person B. They would use person B's public key to write a message that only person B could decrypt with their private key. Once person B decrypts this message, instead of using their public key to send it back to person A, they would use person A's public key to encrypt their message back to person A, and person A would use the corresponding private key to decrypt it. And that's how two-way encryptions with public keys work.